Trig 3D triangles. So in this section here we have to be able to visualize triangles within a given 3D shape. So it'll all be about rotating this image in your head to be able to work out area or lengths of sides or angles within the shape itself. So often we're given a solid shape, such as a cuboid like this, and we could be given the dimensions of the cuboid. And then we could be asked for a point A to G. So say this is A here. This could be the point A, but G could be the opposite point down here. So if we were to look inside or using straws, you can see that it's this orange straw along here. So we would have to be able to see the right angle triangles within the shape itself. So you could actually go down and across to the base, and that shape there would be a right angle triangle. Because if I take it out, I've gone from the top to the ground, so I'm making a right angle triangle. And therefore this would be the point A, this would be the point G, and if that was the point B on the original diagram, this would be the point B, A, and G. And then we could use a bit of Pythagoras then to work out what the length AG was. But of course we would have to know AB and we'd have to know BG as well. So we might need to do another bit of trigonometry looking at the base of the shape itself in order to get the base of this triangle from B to G. Other shapes that we could come across could be our Rubik's Cube. And again, we could be asked for different lengths of sides. So again, you might have A, B, C, and D as your points, the corner points of the Rubik's Cube. And you might be asked to find the side from B to D or something like that. So again, if we look at Rubik's Cubes, like, I mean, really, if you look at the top of that shape there, well, what is it? It's a square. And if you're looking for the diagonal from B to D, then again, what have we made? We've made a right angle triangle. So if we knew the sides CD and BC, again, the diagonal BD would just be Pythagoras. So lovely right angle triangles. Now if we're looking inside, so again, if we were looking at another corner point, A, B, C, D, E, F, G, and then H around the back, we could also be asked from A all the way across to G. So again, if we look inside the Rubik's Cube, again, we can see that right angle triangle shape, because again, we've gone from top to bottom. So we would have a right angle here. And again, we can use our Pythagoras if we know that diagonal across the bottom. Another shape, which is the one we're going to look at today, is going to be a pyramid. And if we look at a pyramid has 4 triangular faces, and then it has a base. And the pyramids of Giza in particular have a square base. So again, if we look inside that shape, and you can use straws to set it up, well, again, you can see if we're going from the top to the bottom and to the midpoint of one side, well, this here makes a right angle triangle, as we saw in the first video. And of course, we could actually go across, if I remove those lines, we could also go from the top to the bottom. And we could go out to this side and go along the green straw, and that would still be another right angle triangle. So it depends on the information that you're given in the question and also what we're looking for, which triangle you'll work with. Okay, so let's have a look at the 2006 question then. So it says the Great Pyramid of Giza is in Egypt, has a square base and 4 triangular faces, and we're told the base is of side 230 meters. So if I mark on my green pyramid up here, we have 230 meters and 230 meters. So each of the square bases is 230. So if we draw the square base, just so we can see. Then that would be 230 meters, 230. The next piece of information we're given is that the pyramid is 146 metres high. So if we look inside that pyramid, so with the straws there, we can see that 146 metres high is this middle orange straw, so the one from the top to the centre of the square base. So it says the top is directly above the centre, right? So we can see that, and we saw that in the video also. So the first thing it wants us to do is find the length of one of the slanted edges, and the slanted edge is marked on that pyramid itself. So we're looking for the slanted edge here, so we could maybe call it L for the slanted length. Now if I look at the straws, that's the green straw there, the slanted length. So what we want to do is see a right angle triangle. So by going from one of the corner points across, I can see that that is on the ground, so it's on the desk, and then the straw is directly up, so that means that must make a 90-degree triangle. So again, if I just draw that, and that's 90 degrees. I know this is 146 metres, and I'm looking for L. So we have a bit of a problem because we can see it's a right angle triangle. We know it's going to be Pythagoras, but of course I don't know what this space here is. So I could call that X. Okay, now that X is this here in the straws diagram, and therefore if I continue that dotted line across to the other edge, that's basically the diagonal, or half of the diagonal I should say, of that square base. So in other words, if I go to my square base, and the center point is the point of intersection of the diagonals, that is X right there. So of course this must also be X. So if I want to find X, which will then allow me to find L, what I want to do is basically work with the square base first and then go to the triangle. So what I would have is my hypotenuse squared is equal to the opposite squared plus the adjacent squared from Pythagoras. Sorry. Zooming in too much. And therefore we have 2x squared will equal the opposite squared, which is 230 plus 230. Sorry, I'll just keep that as the hypotenuse squared because I'm going to half the answer then to get the length. So we're going to have h then is equal to the square root of 230 squared plus 230 squared. And therefore h is going to equal to 325.27 meters. And then if I divide that by 2, x is going to equal to half that distance. 325.27 divided by 2, which gives us 162.63 meters. Okay, so we can now add that to this right angle triangle here. So in other words, this is 162.63 meters. So now to get L, we just need to do Pythagoras. So again, we'll say L squared is equal to x squared, which is 162.63 squared plus 146 squared. So L then will be the square root of all of that. And therefore L, slanted length, is equal to, correct to the nearest metre, 219 metres. So the second part of the question says, find correct two significant figures, the total area of the 4 triangular faces, assuming they are smooth, flat surfaces. So let's look at one of those triangular faces. So what we saw there is we've just worked out the slant lengths, which was 219, correct to the nearest metre, and 219. And we know that the base of the side is 230 metres. So if I want to find the area of the four faces, I basically am looking to find the area of the triangle and multiply that answer then by 4. So at the moment we have 3 sides and no angle. So if I wanted to find the area of the triangle with an angle, I'd be using half AB sine C. So that means I would need to find one of these included angles. And of course, I could do that using the cosine rule. But we saw in the first video that if I go from the top down to the square base along the side of the pyramid, then what I get to is the midpoint of the side. In other words, I make 2 right angle triangles. So now I've actually split the 230 into half, which gives me 115 and 115. So now what you can see is that if I actually work out using Pythagoras, let me take that triangle out. Well, now I could get H. I have 115 metres, 219 metres. And by working out H, this is going to actually be much easier than using the cosine rule, because I can get half the base by the perpendicular height, and again multiply it by 4. So let's work out what this perpendicular height is. Well, we have h squared is equal to o squared plus a squared from Pythagoras. And therefore 219 is our hypotenuse, is equal to h squared plus 115 squared. So sorry, this is the perpendicular height, not to be confused with the hypotenuse there. Obviously we're putting in h, and we have 2 h's. So if I rearrange then to get h on its own, it'll be h squared is equal to 219 squared minus 115 squared. And then to get h on its own, I'll get the square root of both sides. So what that gives me then is a perpendicular height of 186.38 metres. And now if I get the area of one triangle, it's half the base by the perpendicular height. So that's going to be half the base of the triangle. We're talking about this face here, so 230, by the perpendicular height, which we've just worked out to be 186.38. And I'm going to round at the very end rather than rounding and rounding a second time. And then that gives me an area of one face, which is 2,143.7, and that would be meters squared. And then of course for the 4 faces, the area is going to be 4 times that. And to give our answer correct to the nearest meters, sorry, 2 significant figures I should say. So that area is 85,734.8 metres squared. But corrected 2 significant figures. Well, first 2 numbers is 85. The number that follows 5 is a 7, which means I must round the 5 up to the next number, which is 86. So 2 significant figures would be 86,000 metres squared. So nice question that. Okay, so what you're going to do now is you're going to go to your textbooks, and you're going to go to page 250 in book 2, and you're going to do for me question 1, question 6, question 7, question 8, and question 11. And question 7 was from the 2004 paper, and question 11 was from the 2002 paper. So again, nice examples from the past papers.